This is problem number 7 on the practice final. And the problem is you're asked to arrange the following compounds in order of increasing melting point. Indicate what type of solid each material is and which solids conduct electricity. And so we're going to have to be, we need to make the distinction. There is going to be the possibility of an atomic solid, a molecular solid, a covalent network solid, or perhaps or an ionic solid. Did I get an ionic solid? No, okay. Or an ionic solid. And those are in order of increasing magnitude in general. The melting point is going to be determined by the magnitude of the intermolecular forces that are holding those together. And in the case of the ionic solid, we are going to have ionic interactions, ionic bonding interactions. We have a lattice where it's just simple electrostatic attraction, and those have the highest energy. The lattice energy, they can be the highest melting, comparable only to the covalent network solids. So which is going to melt higher, I can't make that call. So I will not expect you to make that distinction. You just have to recognize which is an ionic solid and which is a covalent network solid. Now when we get to the molecular solids, which is going to be the higher melting is going to be determined which type of intermolecular interactions are present. So if there's just London forces present, then it's going to be a very, very low melting material. If there's dipole present, then it's going to be dipole-dipole interactions. That's going to have a higher melting point. If it has dipole interactions and hydrogen bonding interactions, then the hydrogen bonding interactions have the greatest magnitude, and I would expect that the one that has the most is going to be the one that's going to have the highest melting point. And then, after taking that into account, we would look at the general molecular weight. If we're comparing two materials that have the same type of interactions, the one with the highest mass is going to likely have a higher melting point. And so, because it's going to be traveling slower at a particular temperature. So, and then as far as the conduction, ionic solids do not conduct electricity. Molecular solids do not conduct electricity. There is covalent network solids that do, and there's many that don't. Most of them don't, but one that does is graphite. And so that means that we're going to, you're going to know this only because I told you, but if it possibly might end up on the test because we're told. So now let's look at these and see which one's going to be the lowest melting. Well, I've got ammonia and methane. These stay together. The covalent bonds hold them together, and the intermolecular forces that are present are going to be different. So they're going to be only held together by intermolecular forces, and then there's neon, which is an atomic solid. Now, neon can only engage in London dispersion forces, and so I would expect it to be right up front, the lowest melting point. Now let's take a look at the two molecular solids, and now I've got methane and ammonia. These are comparable in mass. This is 16 grams per mole. This is 17 grams per mole. But now this is a nonpolar material. It has no dipole, and so therefore it can only engage in London dispersion forces, which means it's about the same as neon. And now let's compare the two in terms of mass. So now I got to look at the mass of methane versus neon, and well, neon has a mass of 20 grams per mole, and methane has a mass of only 16 grams per mole, which means I would expect the methane to be the lowest melting, and it's a molecular solid. I probably wouldn't care if you got that reversed, but based on that, the type of interactions that are holding these together being the same interaction, London dispersion forces or induced dipole interactions, I would pick methane to be the lowest melting. So I would take, let's see, a different color here, yeah, CH4, and it is a molecular solid, and it's an insulator. Okay, and it would be comparable, but I would put it as lower than neon, which is an atomic solid. And it's so I have neon, which is an atomic solid. These two would be the lowest melting. And I would personally pick methane based on the mass. Now this is definitely going to be much lower than the other molecular solid, which is going to be ammonia. Ammonia is going to engage in London dispersion forces as well. However, it has a permanent dipole, so I've got dipole-dipole interactions, which are going to help attract, but going to give it attractive forces. And also, it can engage in hydrogen bonding, which is going to really raise the melting point. So it's definitely going to be way above that. So I can have two of those in my arrows. And this is a molecular solid. And it's, again, an insulator, which I hope I spelled right. And now that is going to be, these are going to be in turn much lower than the last two options we have. We have graphite and magnesium oxide. And so I'll pick the graphite. And I'm going to say it's about equal to the magnesium oxide. There is no way I could know a priori which would be the higher melting solid. And the graphite is going to be a covalent network solid. It is being held together by the covalent bonds, which are in some sort of almost infinite network, but a very huge network of covalent bonds. And so this is a covalent. Because it's a covalent network of carbon, which is going to be sp2 hybridized in flat sheets of that look like sort of like chicken wire hexagonal rings, fused rings in a flat sheet. And the reason it's so soft is because the covalent bonding interactions are spread out along the sheet, very strong, but the sheets themselves aren't attracted to each other very strongly. And so they slide along each other. Now the conductivity, these are conductive. The conduction occurs through the pi network of pi bonds that occur along the sheet. So the conductivity is very good along the sheets, but not as good between the sheets. They're pretty much bad conductors between the sheets, but they conduct well along the sheets. And so this is a conductor. And this is magnesium oxide, which is an ionic solid. And it is an insulator. And that would be the highest. I couldn't pick which one's going to be highest melting a priori, certainly, unless you happen to have direct measurement. I couldn't predict beyond that. And I wouldn't expect you to.